So as I mentioned, I'm Gillian, and I'm a research fellow at the London School of Hygiene and Tropical Medicine. And today I would like to share with you some of the work I've been doing as part of a fellowship with the Wellcome Trust. And so really, what I've been thinking about is we know asymptomatic malaria is very present in a lot of communities. And whether they're asymptomatic in terms of not having symptoms or they're just parasites, infections with low density, so they're not detectable by routine diagnostic tools. And so this has a lot of implications for health systems because they're just routinely not going to get picked up in that data set. And so this, in a lot of settings, this health system data is used to make for a lot of decision making, for where to put control interventions, for measuring progress, and a lot of these things. And so I really started thinking about what implications does this have in terms of how much malaria we think is around in a community. And so we know malaria immunity is going to really affect whether an infection is going to be detectable or not. With transmission intensity, you acquire immunity through repeated exposure, and therefore it's going to modify the effects of the potential bias that we have in the health system's data. And so really the aim of this work was to determine if there is a relationship between transmission intensity as a proxy for the amount of protective immunity is likely in a population and the proportion of infections that are actually detected within a health system. And so to do this, I started to work with a lot of people to generate a data set of paired community health facility data. So the community data is really cross-sectional surveys, all ages, ideally with PCR, so we can get a sense and an estimate of the total number of infections in a population. And then I also tried to get the health facility data from the same time and space, so matching as much as possible the populations and the temporal bias that we know is going to be present in malaria. And this is just a schematic of what this looks like. So if we look here, so we have our health facility data, and this community survey would represent the same catchment population of that health facility. In settings where they weren't matched up well, like the survey wasn't designed specifically to use the health system catchment area, I used the spatial data that was available to kind of tease apart which populations were the same. I also managed to get covariates to look at potentially adjusting and explaining these associations, and when available, I would use what was collected during the survey. But when it wasn't available, I filled those gaps with the estimates from the Malaria Atlas project through a lot of their surfaces. The next step was really to kind of derive what this proportion detected in health facility variable. So I'm not going to go over the stats behind this, but it was derived variables assuming distributions with the data that I had available. And then this was then used to estimate the probability of being detected in the health facility, which is really just the number of cases that were likely detected divided by the total number of expected cases in that population. We used bootstrapping to estimate uncertainty in this derived variable. And then I used some additive models for the model fit using R. So moving to the fun stuff, the results. I managed to get paired data from 435 clusters across 12 different countries. The map shows the location of those data sets. The cluster level transmission, so by cluster level I mean the paired health facility community pair. The prevalence ranged from 0 to almost 80% PCR prevalence. So it was a good range of transmission intensity, like I said, as a proxy for the population level immunity that you would expect in those groups. So this is what's not going to show because I couldn't put my PDF slides. But the scatter point plots are basically the paired data estimate. So the x-axis is the PCR prevalence, and then the proportion detected within each cluster on the y-axis. There was uncertainty bounds around all of these things, but it's not showing. But I guess imagine that there's quite a lot of uncertainty in the derived variable, as you can imagine, and then the PCR prevalence is not too bad. The red lines is the model fit from the GAM. The confidence intervals were around these, and they are quite wide, especially at the high transmission intensity. But as you can see, essentially the take-home in the full population study is that on average, health facilities will pick up about 20% of infected individuals. But as we would hope that at low transmission intensity, so here roughly below 10% PCR prevalence in a community, you're detecting more of those infections. So as people have less immunity, more people are likely to get symptomatic and therefore go to the facility, get picked up. And so that's good news. There's a lot of scatter, as you can imagine, but there are some facilities that are picking up almost 100% of infections at the lower range of transmission. Interestingly, when I divided it between the two regions, so focusing on Africa and non-African settings, we know the transmission history in these populations is very different. In Africa, we've had a lot of potentially recent decline, but they still have a higher level of population immunity, and you see that result here with just kind of about a flat line. And you really see the uptick in the non-African settings. Again, as we'd expect, they've had lower transmission for a longer time, so they're going to have less kind of baseline population level immunity. And we do get up to almost 100%. Again, this is now trying to explain some of the scatter, because as we can see, there's a lot of variation in a lot of these points. So then I looked at doing the adjusted models to see if we can try to figure out what is kind of affecting these relationships that we see. Again, the confidence bands are not there, but imagine them, they're there, and there is a little bit of uncertainty. But the key variables that were maintained in the model and stayed significant were the probability of seeking care, which again makes sense, because if you're more likely to go seek care, you're more likely to get picked up by the health facility. And also bed net use, which again is probably due to modifying the exposure history of these individuals. So then the next thing that we thought would be really interesting to do is to look at the proportion under 5 and over 5 that are detected within populations. And this stratification was just driven by that's how they collect the health facility data for malaria and how it is recorded. But again, as we would expect, there's a greater proportion of under 5s detected in high transmission settings. This again makes sense. They're more likely to be symptomatic. They're having a lot more exposure. And then in the over 5s, it's a bit flatter across transmission intensity. So just to summarize, I went through quickly, but so on average about 1 in every 5 infections are detected within the health system at higher transmission intensities. And in low transmission intensities, so here showing about less than 10% PCR prevalence, health systems detect up to about half of all infected individuals. There is significant difference in the patterns between African and non-African settings, which is again consistent with the expected levels of population immunity that would be in those populations from their history of exposure. Bed net use and care-seeking behavior did modify these associations. As I said, it again makes sense, because if you're more likely to seek care, you're more likely to get picked up in the health system. And then a greater proportion of infections in the under 5-year-olds are detected in a high transmission setting. This, again, makes sense because of the symptomatic profile, but again, it also could be related to the opportunistic infections that are just detected within health systems. So if everybody with a fever gets an RDT, they may just be positive, but the malaria may not be what's actually causing their fever. So that pattern may also reflect some of these kind of more opportunistic infections in that population. So I have a lot of people to acknowledge. Again, I need to say this work is funded by the Wellcome Trust. Definitely the group that I work with in London, particularly Nuno, who helped me out with a lot of the coding, and Ewan as well, and MAP for providing the covariate data. And then also I'm 100% dependent on a lot of these people for providing the data to inform a lot of this modeling work. Thank you for your attention, and I'm happy to take questions.
Are you going to tell us the paper's open for?
Yeah.
Patrick? Okay, thank you. Chris Plow from Duke Global Health Institute. Thanks, that was a great talk. So the PCR-based prevalence will, of course, vary depending on the lower limit of detection of the PCR. And, that isn't known for some of the published tests. For those that are published, it ranges anywhere from 5 parasites per microliter, which is 5,000 per mil, down to 16 per mil. So 200 or 300-fold difference. Do you and the proportion in those low ranges might differ in these different transmission settings? Do you have a sense of how whether the kind of low density infection prevalences might differ in high and low transmission settings, and how that would affect some of the analyses you're doing here?
So the easy answer is no, but there's a large chunk of this data was from the Mora group, so they do use the ultrasensitive PCR, and so that curve is really going to be, I think, really reflective of that data, if that makes sense. But saying that, I thought about trying to adjust the based on sensitivity level of the PCR, but I haven't found really good published data to compare it to a gold standard to then be able to do that and to estimate that. But again, saying that, the way the models was built, the number of PCR infections in the community was what drove that, the proportion detected as well to a certain degree. So that bias is consistent between both. So I think in my head it's non-differential, so it would not really affect that curve very much. In terms of the specific threshold, yes, it definitely would. But again, this was kind of an opportunistic first pass based on existing data. So I think the trend would be the same, but at a specific point where that curve upticks would change. Patty.
Patrick Walker and Imperial College. It's really cool, the difference between the African and non-African. Was there a difference between care-seeking behaviour on average in those sites? Because that could also give you something, because as you were saying.
Yeah.
And then could you look at, do you have any data on age patterns in those cases in that data? Because that then might give you a clue as to whether or not, if they're more concentrated in children in the African setting for a set level, that might give you some way to back up your hypothesis.
Yeah, and so I guess the first question is, yes, the care-seeking behaviors were different in the African and the non-African settings. One thing to say as well is that half of the studies were research-driven, so a lot of the care-seeking, the passive case detection was a research-driven, so it was good. But that variable didn't stay significant in the models. But if we go back, I mean, if you remember the slides, I can show you them later as well, that the adjusted model, I had the two different lines, so one was African, one non-African, and they were different. Yeah. And then the second question,
age patterns.
Age patterns, yes. And so the age patterns, according to the clinical data, yes, were different, and that was that last slide. In terms of the community, overall, because it was the overall prevalence estimate, the overall estimate would be the same, but I haven't looked specifically at just the infections under 5s, for example, and how that changes, but I could do that.